Alright, let's come back and we start section 5, average value of a function. And let's check the average value for n numbers first, okay? For example, if we have 80 students in our class, then we have the score for each student, right? We have the score for each student from the first one to the 8th one. Then it will be easy to get the average, right? So for example, the average score, the homework score, right? For example, for the homework one we are talking about, so average score, right? Average score. So the YAVE can denote the average score for the whole class. For the whole class. Then how can you get the average score? Then you take each student's score, right? You add each student's score from the first one, second one until the last one, and then you divide it by the total, right? Divided by the total 80, right? Divided by 80 students. So the YI will be the score, the score for the student. That is my notation, right? That is my notation. So the homework score for the students is YI. So you take the sum of the first until the 8th students' homework score in total and divide it by the number of students, 80, you get the average score. And this is the case, okay? This is the case we have 80, right? We have 80 scores. Then we can take the average. So that is called the average value of finite numbers, okay? Finite n numbers. Now let's look at the situation, okay? Let's look at the situation, the temperature in one day, okay? The temperature during one day. So from the midnight 0 until the 24, right? Within the 24 hours. So we know the temperature change, right? Change by time, right? It will change time by time, and you can see minute by minute it change. So you will have infinite temperature readings, right? You will have the temperature readings for every minute, or maybe every 30 minutes. It's different, right? So here there are infinite number of the temperature readings, temperature numbers. How can you get the average temperature during one day? Okay, that is the case when we have the infinite numbers. That is the simple way to understand the infinite numbers. Or you can just call here the temperature about the time. From the curve during one day, you will check that it's a continuous function, right? It's a continuous function, actually. Continuous function. So what is the average value, average function value when the function is continuous? Okay, when the function is continuous. And the previous we have finite n numbers. Actually, that is the discrete case. Okay, discrete case. So here the temperature function is continuous, right? How can we check a function is continuous from the graph? It's connected everywhere, right? It's smooth. There is no hole, no jump or breakout. So the function is continuous. Then how do we compute the average temperature during a day if finite many temperature readings are possible, which means temperature function is continuous, right? Infinite many temperature readings, which means the temperature function T, big T means the temperature about the time T, small letter t, is continuous, right? Is continuous. So that is the question we will solve, okay? And of course, we will use the definite integral to solve that. Now let's check how we get close, okay? How we get close to the definite integral. So we will define the average value of the function, okay? We will define the average value of the function. Now let's establish the framework, okay? Let's establish the framework. So for example, how can we work out or compute? Let's look at the more general problem, okay? Compute the average value of a function y equals fx when x is between a, b, okay? When x is between a, b. Of course, this is a continuous function, right? This is a continuous function f. And then step 1, okay? Step 1, we will divide the interval ab. Divide the interval ab into n subintervals with the equal weights, right? If you are familiar with those steps, you can practice by yourself, okay? Taking the notes. So divide the interval ab into n subintervals. Into n subintervals. And we have the subintervals x0, x1, x1, x2. The I subinterval will be xi minus 1 until xi. And then the last one will be xn minus 1 until xn. Right? With the equal weights, what is my delta x? With equal weights, delta x equals b minus a over n, right? We are familiar with those. So that is the first step, okay? First step. And then step 2, choose the sample point in each subinterval. Choose the sample point in each the sample point x1 star, x2 star, xi star in the I subinterval, and then the last one is xn star. Choose the sample point for each subintervals. Now we have n intervals, right? We have n subintervals, and then we will take the sample point. We will use the function value at the sample point to represent the function from that subinterval. So which means for the first subinterval, fx1 star will be the function value to represent for the first interval. And in the second one, we will choose fx2 star, which is like the height we took for the rectangles, right? We know the function fx will change, but we just choose one function value, right? We just choose one height for the rectangle. Where is the height? At x2 star, fx2 star. So here we formed, okay? So we calculate the average of the function value, okay? Calculate the average of the function values. So the function value will be fx1 star plus fx2 star plus fxm star. How many function value do we have? How many subintervals do we have? N, right? Totally we have N, right? So in this way, in each subinterval, we choose one function value, right? We choose one function value. And here, actually we can rewrite my N, okay? We can rewrite my N in this way. My N can be rewrite as B minus A over delta X, right? N can be rewrite. N is here, just the N is fixed, right? N is fixed. And we know we can increase the number of N later, right? We can increase the number of N later. But N can be rewrite as B minus A over delta X. So I can rewrite in this way. I can rewrite as fx1 star plus fx2 star plus fxn star over B minus A over delta X, right? Over delta X. And then you can shift, okay? Let me just continue at the top, okay? And I know my note is not arranged in a good way, but try to make your note in a clear way. So here delta X can be flipped to the top. So that will be B minus A. I can put the B minus A 1 over B minus A outside as a fraction. So will be each function value fx1 star plus fx2 star plus fxn star times delta x times delta x. What does the second part mean? Each function value times delta x. So what does this part mean? What does this part mean? That is the area, the sum of the area for the nth rectangles, right? We are familiar with this part. So let me just use one more slide. So this formula, okay, this formula. Let me rewrite here. So we continue from the expression 1 over b minus a, and we flip the delta x. We have fx1 star plus fx2 star plus fxn star times delta x. And what does this mean? That is the average. That is the average of the n function values, right? Average of the n function values, which is the sum of all those n function values divided by n. We just rewrite n as b minus a over delta x. We flip the delta x to the top. Then we understand actually fx1 star plus fxn star times delta x, that is the area, right? That is the area. So we can rewrite in this way. Here, by the way, 1 over b minus a. 1 over b minus a is a constant, right? A and b are fixed. This is the constant times this part, so I can remove the constant outside. Then I can rewrite it as the Riemann sum, right? Riemann sum fxi star times delta x. And we know this part is the sum of n approximating rectangles area, right? Approximating rectangles area. Sum of n approximating rectangles area. This part, right? And then here we just assume we take the n average of n function values. But we understand it's continuous function. There will be infinite number of function values. How can we represent that? So we can let the limit n, sorry, then it's not equal, okay? It's not equal again. So this is just the approximation, right? Approximation, you use n function value to represent. Then the average function value of fx, average function value of fx on AB, on the closed interval AB, can be represented in this way. Use the limit, right? Use the limit, let n approaching infinity, 1 over b minus a is the Riemann sum, right? The Riemann sum. And since 1 over b minus a is the constant, right? Constant multiple rule for the limit, you can remove 1 over b minus a outside. That is the limit Riemann sum, right? Limit Riemann sum. And what does this limit of the Riemann sum mean? How can we rewrite this part as a definite integral? According to the definition, this limit of the Riemann sum is the definite integral from a to b fx dx, right? Fx dx. Then we keep the constant 1 over b minus a, right? So what is the average value of a function? Average value of a function. So the FAVE can be defined as a definite integral 1 over b minus a from a to b fx dx. So we can define the average value of a function in this way, okay? In this way. So everyone is clear? And the calculation will be easy, right? Will be easy. Just a constant multiple by a definite integral. So we can define the average value of f of the function fx on the interval ab as this one, right? As this one. Now let's check the examples, okay? Check the examples. And the formula is FAVE equals 1 over b minus a from a to b fx dx. Function is given. Check the lower and upper limit, right? So example 1. Find the average value of the function 1 plus x squared on the interval -1 to 2. It's straightforward, right? So my b is 2, my a is -1, right? So from -1 to 2, what is my function? 1 plus x squared, polynomial, right? Polynomial. So it's 1/3, right? 1/3. And then the antiderivative is x plus 1/3 x cubed from -1 to 2, right? From -1 to 2. And then the final answer should be 2. Calculation is also easy, right? And then let's check one more thing, okay? Let's check one more thing. The mean value theory for integrals, okay? The mean value theory for integrals. So be patient, okay? We might extend it 5 to 10 minutes, okay? Let me just finish this part. This is a last section of chapter 5. Then the next time we can review for the whole chapter 5. Yeah, and we have quiz. Yeah, we have the quiz. So the mean value theory for integrals, okay? For the integrals. We also have the mean value theory for the differentiation. Let's explain the version for integral first. If f is a continuous function on AB, then there exists a number c in the closed interval AB such that fc equals this average value of the function. And we know this is the expression, right? This is the expression for the average value of the function. But now we said that if f is continuous, then there exists a number c such that the function value at the point c that equals the average value of the function. Or in another way, you can move the b minus a on the left side. So the definite integral will be fc times b minus a. How can we understand this formula? I think this part is easy to understand. So this one means the area, the left part, the definite integral is the area under f, under the curve f from a to b, right? From a to b. What does the right part mean? B minus a. B minus a is the weights. What is FC? Here the C is fixed, right? The C is one number. So FC will be the function value, right? So you can also take this one as the height, okay? As the height. So that means the area under fx from a to b, that equals the area of a rectangle. What is the rectangle? The width is b minus a. Then the fc, this function value, will be the height. So the left part means the area of the under the curve from a to b, that equals the rectangle's area, and the height is fc. So we can figure out this fc. And this is the mean value series for the differentiations. Let's review a little bit. Okay, it's the mean value series. We have two versions, for as well as for differentiation and in the integrals. So the mean value series, that is what we studied last semester. Let f be a function satisfy the following two hypotheses. F is continuous on the closed interval AB. F is differentiable on the open interval AB. Then there exists the number c in the open interval AB such that the derivative at c equals, what does this mean? We mentioned that is the straight line, that is the slope of the straight line connecting the two endpoints. The slope of the straight line connecting two endpoints, right? Connecting two endpoints. What is those two endpoints? You can mark it as the endpoint AFA. Point A, big A, point big B, which is BFB, right? That is the slope. This fraction means the slope of the straight line connecting those two endpoints. And so that is there exists the number c. There exists the number c. F prime c means the slope of the tangent line passing through the point CFC, right? So that means the slope. There exists the number c. The slope equals to the slope which connecting the two endpoint straight line, and the mean value series for the integrals. That means there exists the number c. There exists the number c in the closed interval, which gives the function value to make the function value equals the average value of this function, right? Equals this function. So it's about the area for the integrals, right? For the mean value series, in the for the integral version, mean value series for integral version, it's about the area, right? It's about the areas, right? How can you find the c? You just we can work out the average value of a function. It's easy. Then you solve this one, right? You solve this one. You let the expression using c to rewrite the function equal to this value. Then you can solve the c. And then the mean value series for the differentiation. Okay, the mean value theory for the differentiation version, which talk about the slope, right? Which talk about the slope of the tangent line equals the slope of the straight line connecting two endpoints, right? So and also we can understand the integral and the differentiation. They are inverse procedure to each other. Okay. Now let me go through a little quick. So here, okay, here let's check this example again. Okay, and we have already worked out the the average value. The average value will be 2, right? We have already worked out it's 1/3 from -1 to 2, 1 the fx dx, and the average value is 2. So average value is 2. So according to the mean value theory for integrals, there exists the number c. This c is in the interval -1 to 2, such that fc equals 2, right? How can we find this c? You just let fc is 1 plus c squared, right? 1 plus c squared equals 2. What is the c? It's easy to solve. The c is plus 1 and -1. And it's both. They are both in the interval. We are not going to drop on any, right? So c1 is -1. We should care about whether we need to drop, check the interval, right? That is something we practiced last semester. So both solutions are included in the interval. So what does this mean? So the left part, as I said, the left part means the area under the function y plus x squared. And y plus, how can we draw 1 plus x squared? It's pretty easy. You just shift parabola x squared 1 unit upward, right? This is 1 plus x squared. Then the left part is the area under this parabola from -1 to 2. So it's shaded. It's shaded this blue part. And then what is the right side? What does the right side? So that is the either you choose -1 or 1, fc equals 2, right? So that is 2 times 3, right? 2 times 3. What is the 3? 3 is the weight, right? 2 minus -1. So weight is the 3. Weight equals 3. What is the height? The height is FAVG, which is FC, right? Which is the function value at either -1 or 1. So that is 2. So which means the area, this blue part, the area, the shaded blue part, the area equals the area of this rectangle with the width 3 and the height 2. That is what the mean value theory for integrals tells us. It's better to understand the interpretation than memorize the theory. Okay, than memorize the theory. I think it's pretty much for the mean value theory and the average value of a function. Okay, then we will do the quiz. Oh, it's not about the work. It's find the average value of the function on a given interval. Okay, so this is the function g about t. Yeah, the quiz is given now. Okay, the quiz is given now.